Our next speaker is Dirceu R. Rodrigues Jr. Dirceu is a computer engineer with a master's in electrical engineering in control systems, which is awesome because that's what my degree was in. He's worked for a state-owned hydropower plant as an electronic engineer. He won the first place in a public contest, and also as an electrical engineering professor. And also, Dirceu just became my new hero because he was the designer of the first Brazilian electronic color evaluator for roasted coffee. I don't know about you, but if I don't have a cup of coffee in the morning, the day's not worth having. Apparently, it's called Color Gap 1A, and it was produced in 2004, and it's used in quality labs. I'm not sure if that's a quality coffee lab or just quality labs generally. Anyway, Dirceu is going to talk to us about RT-Thread Concurrency for C++ programmers. So, handing over to Dirceu.
Hello friends from RT-Thread community. My name is Dirceu and I work with hardware and firmware design for control systems. This short and introductory presentation is intended to dealing with some aspects of the concurrence in C++ language applied to embedded systems and data acquisition. It has three main purposes. One, to present the benefits of RT-Thread to professionals who already work with that language, usually on desktop world, having interest to start working with a real-time operation system. Two, to serve as a review of some useful C++ techniques and applied it to more hardware-oriented systems. In the process, some comparisons will be carried out with discussion of simple and commonly found cases in the area. Three, finally, an opportunity to work directly with C++ in deterministic projects that use RT-Thread. Okay, let's review an important concept belonging to the theme of this presentation. What's concurrence? In general, we can say that there is concurrence when at least two actions or threads or tasks are making progress, not necessarily simultaneously. The problems we have to solve are involved with data sharing, synchronization, and communication. In today's multi-core systems, this becomes even more complicated because it's not just about moving between one process to another, but actually dealing with things happening at the same time. For example, how to ensure that threads are working with the same data stored in cache memory. Fortunately, as well we'll see, an operation system like RT-Thread provides tools to make the developer's life easier. Let's present a simple example to compare sequential systems with concurrent ones. The three-stage problem is normally given in optimization theory, but we can treat it as a concurrency problem as well. It's asked how long it will take in order to fry three sticks using a frying pan, or CPU here, that only holds two sticks at a time. I required 5 minutes in order to prepare each side. The most obvious solution considered here as the sequential one is to divide the action in 4 tasks, as shown. Note that, as in a real operation system, the tasks have associated states, something as running, waiting, and finishing. First, fray the sides of 2 sticks, do the same thing with the other 2 sides in the next 5 minutes, remove them, and finally fray only 1 stick in the following 10 minutes. So, the total time is 20 minutes. Of course, in this solution we don't use the frying pan efficiently. At the end, the food remains cold. Our so-called concurrent solution involves breaking down task 2 into 2 other subtasks and switching between them in a proper time. It involves removing a stick with a side already done by the other. The total time is reduced to 15 minutes. We agree that is not a very practical action, but it serves to show the concept of stopping one task in the middle and switching to another. Indeed, a context switching. Let's talk a little bit about parallelism. Since the advent of multi-core systems, the true parallelism has been a reality in our daily lives. This is a kind of multiple instruction and multiple data. Parallelism can also occur in the instruction level of a single processor. For example, the single instruction multiple data on ARM processors, such as multiply and accumulate operations typical from the SP field. In parallel systems, the actions are performed really at the same time. For example, in the previous problem, using 2 frying pans, the total time will be just at 10 minutes. I really like to use the right side figure in order to illustrate the 3 processing ways: sequential, concurrent, and parallel. 2011 year brings us the threading support on C++ through the standard template library, STL. Before, that could be accomplished only using specific external libraries. In Unix, besides there was multiprocessing from the beginning, there was no current concept of threads as lightweight process, having less overhead. The famous Boost library uses POSIX threads, or pthreads, for its implementation. In my career, I have had contact with most of these technologies. For example, in the Windows operating systems before Win API, there was the so-called terminate and stay resident program. Since that time, multi-threading support in C++ has greatly increased as versions have been published. Currently, many compilers don't support all the latest features. For example, only GCC 11 supports C++20 semaphores. For that reason, this presentation will be based exclusively on C++ 11, the version on that could be better supported on some other systems. It's worth remembering that determinism and real-time behavior are dependent on the facilities offered by the operating system. Since C++ is just a language making use of that features according to the implementation. But we have to realize that C++ is growing in embedded systems, mainly due to current requirements, for example, in image processing and artificial intelligence. As our time is short, we will make a brief review that will be useful not only for who currently programming in C++, but also for one intending to use it with RT-Thread, for example. The class std thread, based on Boost thread, represents a single thread of execution. Threads allow multiple functions to execute concurrently. It should be noted that, unlike what happens in RT-Thread, we don't have control over time slice or thread priorities here. On the right side, there is an example creating a simple task that takes a parameter. On the left, a usage with a C++ class. Classically, a thread function is implemented as a static function on class, but as shown, it's also possible to do it with a class method through the proper constructor. You can use the same code on multiple architectures, including Windows, where an implementation using Win API takes place. One of the most basic primitives for exclusive access is the mutex. Here in its version, std mutex implements the lock-unlock semantics. Used alone, the mutex has limited application. For example, consider the code below where the idea is to share a buffer between two threads, one producing a set of images and another consuming it. It wouldn't be recommended to share data in this way between a main thread and an interrupt service routine, due to a non-deterministic locking interval. Also, this is not an efficient solution. Besides the mutual exclusion, we are doing a pooling after all. The execution could enter at the critical section just to realize out that buffer is full or empty. There are two important classes that can be used with mutex, which we will make extensive use: lockguard and unique lock. It implements the resource acquisition is initialization technique, meaning the mutex is acquired in the constructor and released in the destructor. The rationale behind them is very simple. For example, these objects can be placed inside loops, being created again in each iteration. the condition variable is implemented in most high-side architectures. Like the previous classes, it also depends on a mutex. But now we have a notification and waiting system without consuming processor time while waiting for a given condition to occur. In other words, no pulling. The thread blocks in wait for, or wait until methods releases the mutex while waiting for the condition. On the other side, the methods notify1, notify_all allow to wake up the waiting threads. Then the method wait returns and the mutex is atomically reacquired and stays so until the end of the block or when intentionally released. Lockguard can be used with notify methods, but not with wait ones. This makes sense because lockguard doesn't perform the unlocking needed by wait. The companion example is an improvement regarding the previous one. Here, a high-speed serial port decoder, not the checking for a condition after the return of wait method. This deals with a spurious wake-up problem. What's the spurious wake-up? It happens when a thread wakes up from waiting for a condition variable only to find that the condition it was waiting for has not been satisfied. Could be happen due to two reasons. The condition variable was notified and when the waiting thread finally wakes up, another thread ran and changed that condition. Or simply a waking up without a real notification at all. It's a good practice to implement that checking in a loop. It has an additional advantage. Also deals with the lost wake up. We know a notification works like a pulsed signal. In this case, the calling of wait could be done after the notify execution. In other words, the notification is lost. Next, an example using two condition variables around on mutex. One of them to wait notify the buffer not empty situation, and another similar to handle buffer not full. The producer thread waits for enough space in the bounded buffer. When this happens, it places an item in the buffer and notifies a potential blocked consumer thread, waiting for a non-empty buffer event. A similar situation occurs with the other thread, which wakes up a producer thread blocked due to a foul buffer. Note that handling for spurious wake up around each wait. Semaphores are part of RT-Thread RTOS. But as I already mentioned, C++20 semaphores are only available in GCC 11, but that doesn't mean that this important synchronization mechanism cannot be built with other classes already presented. Here, I show a simple class implementing semaphores, very well known online. Semaphores are useful when there is a certain amount of resources of the same type, which can be reserved by threads for processing. The idea is to adjust the semaphore value according to the number of the available resources. A thread acquiring a semaphore wait decrements this value atomically. If it reaches 0, the corresponding thread will be blocked. After a thread uses resource, it can release it signal. So the associated value ends up incremented and a waiting thread will wake up. Note the need for additional mutex in this example in order to provide exclusive access to the resources. Remember that in the condition variable case, the mutex is automatically reacquired when wait returns. Finally, here the threads are created using lambda functions rather than the traditional way. Waiting for more than one event using a condition variable is an easy task. It's enough to create notifications for each event and increase the checking list in the while loop associated with the wait method. These notifications can be spread for the whole code. In the present example at TCP client, an event is also provided in order to inform the thread run to terminate, stop. This type of mechanism is useful to have control of thread lifetime. The following is an example of timer to illustrate waiting on a condition variable using a timeout. We are helped here by the chrono library. Difference of wait for the variant wait until distinguishes between spurious wakeup and timeout occurrence. Here, the thread run works periodically, but it can also listen to a stop event. The key point here is the comparison with the enumeration stdcv status timeout. Next, other example regarding wait until. The task EC waits for three conditions or events: an EC packet arrival, an EC timeout, and the task termination. RT-Thread. It's not an older RTOS. It's not only a real-time kernel, but also has a rich middle-tier component, suitable for several architectures, including non-microcontrollers. Added support on asymmetrical and symmetrical multicore systems. It's open source, written in C, such as Linux. Nano version for constrained devices. A complete set of development tools like RT-Thread Studio. The great news for us is that RT-Thread also supports the C++ threading system and the pthreads, or POSIX threads, as well. See this figure of the RT-Thread Studio software, showing an example of configuration. Thus, it's also possible to write the C++ applications for RT-Thread and take advantage of material presented on first part. Of course, the most direct and useful way to make concurrency on RT-Thread is using the tools provided by the kernel. There are plenty of support for managing time, memory, interrupts, thread communication, and so on. Next, we introduce the functions related to thread synchronization, namely mutex, semaphore, and event. Now let's talk about the features of the threading system. The biggest difference between C++ threads is that here it's possible to set priorities for individual threads. RT-Thread offers up to 2056 priorities, where 0 is the highest one. It should be noted that the thread with the highest priority is the one that runs, unless it's blocked. When more than one thread has the same priority, a round-robin mechanism is performed. It's also possible to specify the time slice of each thread, and when this time runs out, a context switch is performed to another thread of equal priority. The thread priority associated with the main function can be changed too. The figure shows the different states of the threads as well as some control functions. Several RT-Thread kernel system objects can be created in two ways: dynamic and static. The current example shows how to create a thread dynamically with a parameter passed for it. So, using RT-Thread create function, the thread handle and stack space are dynamically allocated from the system stack. On the other hand, using RT-Thread init function, the thread handle and stack space are statically allocated from the user code. Mutex is a binary semaphore. Unlike semaphore, it can only be released by the thread holding it. The mutex is a unit to priority inversion problem. This situation can occur when a low priority thread is using a resource and a high priority thread is blocked because it also wants to use that resource. An intermediate priority thread that has nothing to do with the resource ends up running wrongly. The order of the NQE blocked threads can be respect the timeline or the thread priorities. Finally, the mutex supports recursive access, where the thread can acquire the mutex multiple times without being suspended. The mutex take and mutex release functions are equivalent to std mutex wait and notify from C++. The following is a previous example of C++ converter for use with RT-Thread mutex. A timeout between 0 and infinite can be provided when calling the take function. The return value can be used to identify the success, timeout, or error. A 0 timeout is equivalent to a peak function named try_take. Event set is order of the mechanisms for synchronization between threads. Event send and event receive. A thread is blocked waiting for one or more events to be received. We had reached a similar effect on C++ using a condition variable. Do you remember? An event set can contain multiple events. There is no data transfer involved. Sending the same event to the thread multiple times is equivalent to sending only once. Events can be combined by the logical AND and logical OR operation, meaning that the arrival of an event would be enough to wake up a thread or the occurrence of all of them. A 0 timeout is possible too. The companion code shows a synchronization between two threads, task LED and task button. The first button press causes LED start blinking and the next turn it off. Differently on C++11, the RT-Thread implements semaphores. Do you remember the previously presented class semaphore having the methods wait and signal? The behavior is very similar. On RT-Thread, that effect is obtained through the send_take and send_release. Such as other synchronization mechanisms, a timeout for waiting can be specified too. Okay, that's all, folks. So, good luck using RT-Thread and C++ in your next design. Thanks for watching.